Here's another integral that we want to try to evaluate. Within any integral, as I've been saying in some of the other videos, you hope that a formula for an antiderivative works directly. That doesn't really seem to be the case here. Then you would hope you can do algebra and have a formula work. Doesn't seem to be the case. Can a u substitution work? Well, the logical choice for u here would seem to be this quantity under the root. Now, if you let u equal 9 minus x squared, you're going to pick up a 2x in your derivative, but there's not going to be the proper cancellation occur because you've got an x squared here and you only have an x to the first in that derivative. So it doesn't really seem like a u substitution of what's under the radical will work successfully. Now, this radical does involve a difference of squares underneath it. And whenever you have a radical that looks like that, oftentimes a trig substitution will let you successfully get to the point where you can evaluate the integral. So the substitution that would be suggested when you have a root that looks like this one does, so I'll just kind of write out the formula I'm about to apply. When you have a root, let me try that one more time. When you have a root of the form a squared minus x squared, a substitution that will successfully rationalize that expression, get rid of the root, is going to be if you let x, so this doesn't equal anything, I should have drawn an arrow there, struggling a little bit here, sorry about that. If you have this root, this type of root, and you want to try to rationalize it to get rid of the root, try to let x equal a sine of theta. So for our purposes, a squared is 9, meaning a would be 3, and we would be trying to let x equal 3 sine of theta. So what you're going to do is you're going to take the original integral and let x equal 3 sine of theta. So we're going to have a 3 sine of theta go in place of the x that's in the denominator, and that x is being squared. We're going to have to replace dx with something that it equals involving a d theta, and we're going to be able to generate that with this equation here in a minute. And then we're going to do a little bit of algebra with this root and figure out what it transforms into through this substitution, and that's going to go in this numerator in just 1 second. Let's get the dx in place first. So we need to know what dx equals, and you can take the derivative of this x with respect to theta. Right, the derivative of x with respect to theta is going to be, well, it's going to have that constant 3 in it, right? So we're going to copy that constant 3, and then the derivative of sine is cosine. So what does dx equal? What can you replace the dx with? We want to replace this dx with something. Dx is going to equal 3 cosine of theta times this d theta. So this is what we're going to have going in place of the dx right here. So 3 cosine of theta d theta. At this point, we want to do a little bit more legwork to try to simplify this root. Okay, so we let x equal 3 sine of theta. What happens to the root if we let x equal 3 sine of theta? Well, if you put 3 sine of theta in place of this x and then you square it, the 3 is going to become a 9, and then the sine is going to be squared. So we'd have this expression. Now, you can't just take the square root of this 9 because this is a difference under the root, right? But if you can somehow factor what's under the root, and here we definitely can, we can take out a common factor of 9 between these two terms, then you're going to be able to do the root of any of the pieces, any of the factors that you know the root of. And we do know the root of 9 is 3. Now, you still have a difference here. Because this 1 minus sine squared theta is 2 terms, we can't do the square root of the 1 and then the square root of the sine squared. But what we can use is we can use the Pythagorean identity. And the Pythagorean identity, I'll try to fit it in right here, says this: cosine squared of theta plus sine squared of theta equals 1. Well, if cosine squared theta plus sine squared theta equals 1, doesn't 1 minus sine squared of theta, if I'm moving this to the other side, 1 minus sine squared of theta equal cosine squared theta? And that's going to allow us to put cosine squared of theta in place of 1 minus sine squared of theta. Now you have a single term. It is a perfect square. Cosine squared is a perfect square, and the square root of a perfect square is always able to be done. We're going to get cosine of theta for that root. So the root simplifies to 3 cosine of theta. So in this numerator, I'm going to have what we just simplified the root to, 3 cosine of theta. Now we want to try to simplify this a little bit. So I'm going to do all my work within the integral here. This was just kind of some scratch work that we were doing to carry out the substitution properly. And now we're ready to try and see if we can develop an expression here that we can actually find the antiderivative of. So let's see. I'm going to square this quantity in the denominator, and that's going to give me a 9 sine squared of theta, and then I still have the 3 cosine of theta d theta here. I kind of left this 3 and this 3 there, but I was kind of anticipating that I would be able to, once I squared this 3, cancel the 3 times the 3 with the 9 that's in that denominator. And if I multiply cosine of theta times cosine of theta, my integral looks like this: cosine squared theta over sine squared of theta. And I'm trying to do this integral with respect to theta, right? So the d theta is the only thing left outside the fraction there. Well, let's see. Cosine over sine. You're more familiar, I'm guessing, with sine over cosine. Sine over cosine is tangent. But cosine over sine is the reciprocal of tangent. And the reciprocal of tangent is cotangent. So cosine squared over sine squared can be re-represented as cotangent squared. And there is a way for us to actually evaluate the antiderivative of cotangent squared. If you're one of my students, this isn't something that we really explored a lot. Depending on who exactly you have for calculus, you might be expected to know this. I wrote the Pythagorean Identity up here a few minutes ago, right? Cosine squared plus sine squared equals 1. If I divide everything in this equation by sine squared, what ends up happening? Well, if I divide everything by sine squared, I get cosine squared theta divided by sine squared theta plus sine squared theta over sine squared of theta equals 1 over sine squared of theta. I don't know why I'm writing on a slant all of a sudden here. Sorry about that. So I've basically taken the Pythagorean identity and I've developed an equivalent form of it. I've divided everything in the Pythagorean identity, both sides of the equation, by sine squared. This right here is cotangent squared. What we have here is 1, right? Sine squared over sine squared is going to be 1. And then this is 1 over sine squared. Well, 1 over sine is cosecant, so that's actually cosecant squared of theta. Why is this beneficial? Well, you notice this has a cotangent squared in it. If we want to solve this for cotangent squared, what we can do is we can write it as cotangent squared of theta equals cosecant squared of theta minus 1. Now, if I replace this expression with cosecant squared of theta minus 1, check out what happens. Cosecant squared of theta, whoops, a little early on my square there. Cosecant squared of theta, d theta, is an integral we can do, minus the integral of 1 d theta, which is another integral we can do. So I've replaced cotangent squared with cosecant squared minus 1. We can do this integral. There's an integration formula for this. The antiderivative of cosecant squared is always going to be negative cotangent of theta, and then minus the antiderivative of 1 with respect to theta. Well, the antiderivative of a constant with respect to theta is going to be that constant, 1, times the variable theta. This is an antiderivative, so we're going to tack on our plus c. Now, like I said a minute ago, if you're in my class, I wouldn't really expect you to know this little sneaky sequence of steps here to manipulate the integral to do what we just did. But depending on who you have for calculus, you might be responsible for that. We now have an antiderivative. No more integral symbols. We next need to figure out a way to get the original variable x back into our answer. So if we scroll back up here, we had originally stated a long time ago that x was going to be equal to 3 sine of theta. If I take some space in the bottom corner here, I'm struggling with straight lines right now, sorry about that. If we take some space in the bottom corner with x equals 3 sine of theta, what you can do with this equation is you can solve it for sine of theta. Divide both sides by 3, and you have x over 3 equals sine of theta. Why is that beneficial? Well, that lets you draw a right triangle. If we call this the angle theta, we're saying that sine of theta is equal to x over 3. From SOHCAHTOA, sine would be opposite over hypotenuse. So opposite the angle theta, I'm going to have x units, and then the hypotenuse of my triangle is going to be 3 units. How would I get this side? Well, I'd get that with the Pythagorean Theorem, right? I would have this squared equal to x squared plus whatever this side is squared. So if I do 9 minus x squared, right, this side squared minus that side squared, and take the square root, I'm going to have solved for my last side of that triangle. So we have a triangle here that involves the angle theta. We have all 3 sides labeled. Why is that beneficial? Well, cotangent is going to be adjacent over hypotenuse, right? Tangent is opposite over adjacent. Cotangent's the reciprocal of that. If I look at this and I take the side adjacent and divide by the side opposite, I'm going to be looking at the square root of 9 minus x squared over x, right? Adjacent to the angle theta divided by the side opposite the angle theta minus, we do have to do something a little bit different to get this out of there, but it's almost done. To figure out what theta gets replaced with, well, we've said here that x over 3 equals sine of theta. Won't that mean that the inverse sine of x over 3 is going to equal theta, right? Just solve that for theta. So we're going to replace the theta with inverse sine of x over 3. We used a trig substitution, involved a little sneaky trick to get to the point where we could evaluate this antiderivative, but we were finally able to evaluate an antiderivative, and there it is. Trig substitution. Those are always fun.